What is electric potential? Imagine you have a charged particle, say a small positive test charge. This charge exists in an electric field created by other charges. The key question we want to explore is: how much is the electric field pushing this charge in terms of energy per unit charge? That's where electric potential comes in. You can think of electric potential as the pressure in an electrical system that drives charged particles, similar to how water pressure pushes water through pipes. In fact, electric potential, measured in volts, represents the amount of work done to move a unit positive charge from a reference point, typically at infinity, to a specific point in an electric field without accelerating it. For example, think of gravitational potential energy. If you lift an object in a gravitational field, like raising a book off the table, you are giving it more gravitational potential energy. The higher you lift it, the more work you've done against gravity, and the more energy is stored. Now, let's switch to electric fields. Suppose we have a positive charge near another large positive charge. Since similar charges repel, you have to do work to bring the test charge closer. That work is stored as electric potential energy. But electric potential energy alone isn't the best way to describe what happens to different charges, because different charges feel different forces. Instead, we define electric potential, V, where the equation looks like this, where W is the electric potential energy, and Q is the charge. This tells us how much energy per unit charge is available at a point in space due to the electric field. To get a clearer picture, let's look at how we derive the formula for electric potential. From the given equation, the next step is to calculate the work done in moving a charge within an electric field. We must consider the force acting on the charge. This force is given by the product of charge and field intensity. The work done on the charge when it moves a distance in the direction of the electric field can be defined as. If we consider a uniform electric field, this simplifies to. Substituting this back into our formula for electric potential gives us. This derivation illustrates how electric potential increases with distance in a uniform electric field, indicating that to move a positive charge away from a negatively charged source, or toward a positively charged source, you need to do work against the electric field. This concept closely ties into electric potential energy, which refers to the energy stored due to an object's position in an electric field, much like gravitational potential energy, increasing as you move a charge higher in an electric potential. It's important to note that electric potential is a scalar quantity. It only has magnitude in no direction, unlike electric fields, which are vector quantities. This distinction is crucial for understanding other electrical phenomena, from how batteries work to the dynamics of circuits. What matters in most practical applications is the difference in potential, or voltage. This tells us the work done per unit charge when moving between 2 points. On the other hand, the electric field can be expressed as the rate of change of electric potential. This means that in regions where the potential changes rapidly, the electric field is strong. Here is an example. Imagine a parallel plate capacitor, where one plate is at plus 10 volts and the other at 0 volts. If we place a positive charge near the higher potential plate, it will naturally move toward the lower potential plate, just like a ball rolling downhill in gravity. This movement is driven by the electric field, which is always directed from high to low potential. That's why we define current in circuits as moving from higher to lower potential. If you found this explanation of electric potential fun and enlightening, don't forget to hit that like button, subscribe, and ring the bell for more exciting insights on electrical engineering theories.